I'm Solomon Azameti from Biomedical Engineering Group 9, and my group and I will be taking you through problem 1.9 in the reference book, and that deals with how to convert high-order differential equations to signal flow graphs. So in control systems engineering, the systems are mostly represented by high-order differential equations, and those system of equations describes how the system behaves over time. But the equations become tedious to analyze and compute manually when the order of the differential equations tends to become higher and higher, and so we'll be learning how to convert them to signal flow graphs. So every differential equation, every higher order differential equation can be converted to signal flow graphs by some laid down rules and procedures that we learn. Alright, so those signal flow graphs will help us to easily analyze manually how the systems are behaving, the various feedbacks in the system, and how to manually operate the system and then compute the values, analyzing how it would operate. So in converting some of the integrals to the lower order differential equations, there are transmittances, which are the gains along the signal flow graphs. So with those ones, when we negate the gain of the feedback, then that also affects the incoming signal to its source and then the outgoing signal to its source. So that will be basically what we will be doing in this very presentation. So my group and I, they will do justice to some 3 questions that will give us the full understanding of how to actually convert a high order differential equation to a signal flow graph that helps engineers in easily analyzing of systems.
Thank you, Solomon. Good day, everyone. I'm in the person of Mind Kelvin Malloy, and I'll be taking you through what signal flow graphs actually are. So, what are signal flow graphs, if you may ask? Signal flow graphs are simply directed graphs. So, directed as in each connection in the diagram has an arrow, and these arrows show you where the signal is traveling to in the system. So to comprehend what signal flow graphs are, you need to understand 3 basic components of signal flow graphs. So 1 being the nodes, 2 branches, and 3 gains. So the first one, nodes. So in our signal flow graphs, the nodes are the circles, and these circles represent variables in the equation. For example, you'd have y prime, and at a single stage in the system, each node has a single value. So second, we have the branches. So the branches, they are simply arrows connecting one node to another. So if we have node A and node B, and we have an arrow connecting node A to node B, that is a branch, and it simply tells you that the variable at A influences the variable at B. So the third one are the gains. So if we have an arrow, the arrow is going to have a number, and that number is going to be the gain. So the gain is just the coefficient of the terms in the original differential equation. So if the coefficient is negative, the gain is also negative, and it can also be called negative feedback. So how do we actually build signal flow graphs from differential equation? So we have a method, and the method involves 3 steps. So 1, you rearrange the equation such that the highest derivative is on one side, so you make that the subject. Then secondly, you integrate downward step by step such that the integration yields the next lower derivative. Then step 3, every remaining term in the equation becomes a feedback branch, simply meaning it's going to be reversed, with the coefficient being the gains and their signs being preserved. So with this, our next presenter, Chachu Walter, will now apply this method in building our first signal flow graphs from a differential equation. Thank you very much.
My name is Walter Chachu, and I'll walk us through the setup for part I, which is our second order differential equation. So the equation given to us is y prime prime plus 10y prime minus 5y equals 3x. Our first step is always to isolate the highest derivative, which in this case is the y prime prime on one side of the equation. So by rearranging the equation above, we have y prime prime, which is equal to 3x plus 3y minus 10 y prime. This setup is the most important one because the highest derivative becomes the input node. That's the very starting point of our signal flow graph. Moving on to step 2, we then define our node variables. So for this second order equation, we have 3 nodes, which are x1, which is equated to y prime prime. This is our input node, the highest derivative. And then we have x2 to be equal to y prime, which is the integral of x1 with respect to time. The last node is x3, which is equal to y, which is the integral of x2, and our final output. The chain is simple in the sense that we start at y prime prime, integrate once to get y prime, integrate again to get y. Each integration becomes our integrator block with a gain of 1 over s in the signal flow graph. We can also already read the feedback directly from the graph from the rearranged equation, which is the positive 5 from y and the negative 10 from y prime. The rearranged equation tells us everything, which entails the nodes, the integrators, and the feedback all in one line.
Thank you, Walter. I'm Precious Sano, and I'll explain to you the signal flow graph for the second order equation. First, let's start with the forward path, which is the main signal pathway from input to output. And from the equation that was given to us, our signal moves from x to y double prime to y prime and then to y. So from x to y double prime, we have our gain being equal to 3. And this is because 3 is the coefficient of x. Now, from y double prime to y prime and from y prime to y, we have integrators. And in the frequency time domain, we have our integrators gain being equal to 1 over s. So from y double prime to y prime and from y prime to y, we have the integrator gain being 1 over s. Now, let's talk about the feedback. Using our new arranged equation, which is now y double prime, which is equal to 3x plus 5y minus 10y prime, each term on the right hand side, apart from the x, will now become a feedback branch that will loop back into the y double prime. So a gain of plus 5 from y back to y double prime will be a positive feedback that will add to the signal. And a gain of minus 10, which is from y prime to y double prime, will now become a negative feedback, which will oppose the graph instead. Which will oppose the signal instead. So now we've talked about 2 forms of graph. The first one is the reversal form that we use to construct it, and the second one is the linearized one. Both represent the same graph system. And now remember that always, apart from the highest derivative, each term will become a feedback branch, and the coefficient is always the gain. So now Michael Kwashi will introduce our second branch to you. Thank you.
I'm Max, and then we're talking about the signal flow chart. So we're given the fourth order differentiation. Y prime prime is equal to x, which is equal to y4 prime plus 6y3 primes plus 5y double primes plus 3y prime plus 2y, where x is the input and then y being the output. So this is how we are going to go about the equation. The highest derivative is being isolated, which when it is being done, we are going to get y4 prime is equal to x minus 6y prime minus 5y prime minus 3y prime minus 2y. So the multipliers are therefore going to be served serving as the gains, with the primes being integrated into its simplest form. So when we are done, we are going to get the gains: -5, -6, -3, -2, and the multipliers, which are going to be integrated into the list, which is going to be y. Then we are going to do our signals. Thank you.
My name is Hachampan Mami Kisiwa, and I'll be explaining the signal flow graph for this fourth order differential equation. This is because the equation is of fourth order, so we have more derivatives involved in the system as compared to the previous examples. The nodes are connected in a chain as follows: x to y quadruple prime, then to y triple prime, then to y double prime, then to y prime, and then finally to y. So essentially, the signal flows step by step from the input all the way to the output. The input gain from the x to y quadruple prime is 1. Well, this is because in the original equation, x appears the coefficient of what? Of 1. Between every consecutive pair of nodes, we place an integrator with a gain of 1 all over s. Since this is a fourth order equation, we have 4 integrators connected in series. Each integrator represents one level of integration as we move from the highest derivative down to the output of y. Now, let us please consider the feedback branches. All 4 feedback branches return back to the y quadruple prime node, which is the highest derivative node. The gains of these feedback paths are taken directly from the rearranged equation. We have -6 from y triple prime, -5 from y double prime, -3 from y prime, and -2 from the output of y. All these feedback gains are negative. This makes so much sense because in the rearranged equations, all these terms are subtracted on the right hand side. Finally, the slides show the reversal form first, followed by the cleaner linearized version. This helps us clearly see the structure of the system and how it matches the mathematical equation. Overall, we can observe a clear linear pattern. The order of the OD equals the number of integrators and also equals the number of feedback branches. All this pattern works consistently for the higher order systems. Thank you.
Thank you, Kiswa. My name is Seth Ankima Owusu, and today I'll be taking you through the part 2 of our question. The part 2 of our question is the y prime prime plus the 3y equals x. And with this, we notice something unique about this equation, which has no velocity term or the y prime term. Our goal is to map the logic behind this signal flow graph to visualize how the system components behaves without the damping components, which is the y prime. So step 1 is always to isolate our highest derivative. So by rearranging the equation, we have y prime prime equals x minus 3y. This tells us that the acceleration y prime prime is a sum of our inputs x and a negative feedback from our position y. This whole rearranged equation serves as the entire blueprint for our entire signal flow graph. Next, we define our nodes. X serves as our inputs, followed by y prime prime, which is our starting points, then to y prime, and finally to y. To move from y prime prime down to y, we pass through 2 integration stages. Although y prime doesn't exist in our equation, it must exist as a node between our 2 integers because we can't get to y without passing through y prime. For the critical part, which is the feedback loops, since there is no y prime term, there is zero feedback from the y prime node back to the start. We draw only a feedback loop from the y term back to the y prime prime with a gain of -3. This acts as a restoring force for our system. Thanks for joining our deep dive into part 3 of our question.
Thank you, Seth. Good day to you all. My name is Anita Baba Miles, and I will explain the signal flow graph when a derivative term is missing. The fourth part looks the same as part 1, and that is 2 integrators in the chain, and it moves from x to y prime prime to y prime and then to y. The input gain is 1, and it has 2 integrators each with a gain of 1. That structure does not change. It is still a second order equation, so we still have 2 integrators. but the feedback is where things change a little, because y prime does not appear in the original equation, and there's no feedback in the y prime node. There's only one feedback branch in this graph, and it is from -3 to -3 from y back to y prime prime, and that's the only feedback, nothing else. The y prime node, that is x2, still exists. It must exist because it is part of the integration chain from y double prime down to y, but nothing feeds back from it because the original equation never used y prime as a term. And then when you compare this to part 1, which had 2 feedbacks, one from y and one from y prime, here removing y prime from the equation removes its entire feedback branch from the graph. This graph mirrors the equation exactly. A missing term in the equation is equal to a missing feedback branch in the graph. The graph never lies about where it comes from. Finally, Samuel Partin Dakwa will now summarize everything we've covered today. Thank you for now.
Thank you, Joanita. My name is Partin Samuel Dakwa, and I'll bring today's presentation to a close. Across all 3 examples, we use the exact same 5-step method every single time. Let me walk you through it one final time. Step 1, solve the highest derivative. It becomes the input node of the graph. The step 2 is you have to define each lower derivative as a node. Work downward from the highest to the lowest. Connect consecutive nodes with integrators. Each integrator has gain 1 over s in the frequency domain. Step 4, every remaining term in the original equation becomes a feedback branch. The coefficient is the gain, the sign is preserved exactly. Step 5, verify by reading the graph back as an equation. If it matches the original, then the graph is correct. So from our 3 examples, we also confirm 3 important observations. First, the order of the differential equation always equals the number of integrators in the graph. Second, a missing derivative term is in the equation means a missing feedback branch in the graph. Third, the signal flow graph is not something separate. It is the same equation expressed as a picture. Looking ahead, signal flow graphs are the foundation for applying Mason's gain formula, which allows us to calculate the transfer function of an entire system directly from the graph, without having to solve the differential equations all over again. That is the real power of what we learned today. Note this, signal flow graphs convert complex differential equations into simple, readable visual systems, making analysis faster, cleaner, and much more powerful. On behalf of Group 9, Biomedical Engineering Year 3, thank you very much for listening.